This video is on power models. Power models actually follow the same concept as just direct and inverse variation. So power models are the same concept as direct and inverse variation. The difference is that we are going to have exponents that are larger than 1. So for example, direct variation was y equals k times x, where k was the constant, x is the variable. And in this case, since it's a power model, it's going to have an exponent. We're going to have an exponent on the x value, or on the variable. We're going to put that as r. That's our exponent. And for inverse variation, we know that the equation for inverse variation was y equals k divided by x. And in this case, we're going to have an exponent or a power on the x again. So it's going to be k over x raised to the r power. Now with these, because it still follows the same concept as direct and inverse variation, the power model for direct variation will still go through 0, 0. So it still goes through 0, 0. It has to have a y-intercept of 0, 0. And it's still a continuous graph. The difference being is that it now might be curved instead of linear. For inverse variation, it still has no meaningful y-intercept. So it still has no, I'm just gonna put no y-intercept, but it's that meaningful y-intercept. And inverse variation as power models is still a discontinuous graph, which means it will be split. We still write the sentences and the equations the same way we did for basic direct and inverse variation. So we have two examples right here on just write the sentence from the equation. If we know what the variable stands for, you should say the word that it relates to. So for this one, we have r is the radius and a is the area. So the radius is equal to the square root of area divided by the square root of pi. So again, we need to determine if this is a direct, inverse, or neither. And we focus on, is our variable on the top of the fraction or in the bottom of the fraction? Just because we see a fraction does not automatically mean inverse. We have to actually determine if it's based on where the variable is located. So area is our second variable. We have radius completely alone, so that helps us know that we can determine direct or inverse. Area is actually on the top, so that means that this is a direct variation. So I'm going to put direct, and now we want to know what our k value is. Now our k value is our constant. There's always a top number and a bottom number. So our top number is actually a 1 because it's a 1 times the square root of area divided by the denominator. The actual number on the denominator is that square root of pi. So we have to keep that symbol with it. Square root of pi. So that's our actual constant. So when we write our sentence, we'll put radius varies. Radius varies. It was direct variation, so directly with. Now, it's not just area, it's the square root of area because we do have this symbol on our area. So I'm going to put with the square root of area. And again, this goes back to why it's a power model, because it's not just area, it's the square root of area. And if you remember, the square root can actually be written as a power of 1/2. This is why it would be a power model. Then we also still have our constant, so with the square root of area with a constant of. Our constant was 1 divided by the square root of pi. So again, what it was actually directly proportional to was the square root of area. And this is what gives us the power model. It's not just area, it's the square root of area. It is important to know which part is the power model and which part is just the direct variation. The square root is what made it into a power model. On this next one, the I stands for intensity and then the X stands for distance. So again, these are our two variables. I is by itself and then X determines if it's direct or inverse variation. So in this problem, since the X is in the denominator of the problem, this is an inverse variation. And then we want to find our constant. Our constant is all of the numbers. So our top number is 160 divided by, the bottom number is pi. The square is a power, so it is not part of your constant. The squared is attached to your variable. So the number that's on the denominator is the pi. So our constant is 160 divided by pi. So to write our sentence, the I starts first, so its intensity varies. Intensity varies, and varies inversely with, so it's not just x or distance, it's the square of distance, not the square root. A root is the radical, but it's the square of distance, or we can call it distance squared because it's the word distance squared. So with distance squared. Again, this is why it's a power model, because you have the exponent of 2, so that's why it's squared. So intensity varies inversely with distance squared, with a constant of, our constant was 160 divided by pi. So again, the part that made it into a power model was the fact that it was distance squared and not just distance. So distance squared is what gave us the power model. On these next two examples, we want to write the equation. We write the equation from the sentence. So on these, when we're given the equation, we have what our constant is. We can either see that it's a 1 or it will tell us that it's k. But if you're given a full-on equation, you know what the constant has to be. In a sentence, if it tells us the constant, we know the constant. But if it does not tell us the constant, we have to keep the letter k for our constant. So for this first one, it says time is inversely proportional to the square root of height with a constant of 2. It actually does tell us our constant, so we know what k is equal to. So let's go through this. It says time is, that tells us that that's our first variable. Then it says inversely proportional, so we know we're going to have a division, to the square root of height. It's not just to height, but it's the square root of height. That's what gives us our power model again, with a constant of 2. So again, it's time is, so that means we're going to put t equals, so I'll just use a lowercase t for time. T equals. It says inversely proportional, so we know we're going to have division. Our constant should go on top, so it says with a constant of 2. Here's our 2. So it says it's inversely proportional to the square root of height. So it's not just height, it's not just h, it's going to be the square root of your h. So we'll put the square root of h in the denominator. And this is our equation. On the second example, it says force varies directly with the cube of mass. It does not tell us our constant. So what that means is we have to continue using k because we don't actually know what our constant is. So it says force varies. That tells us what we start with. It says directly, so we know it's multiplication. And then it says the cube of mass. Not just mass, but the cube of mass. That's what gives us our power model. So force varies means F equals. So I'll just use the capital letter F equals. We would have our constant next. As always, we always put our constant right next to it. But in this case, we don't know what our constant is, so we have to use that letter K to represent our constant because we don't know what it is. Directly means it's going to be a multiplication, not a division. It says the cube of mass. It does not say the cube root. There is no radical. It's just cube of mass. So what we can do here, this is just mass cubed. So a letter for mass could be M. And then we want to cube this M. Not cube root, but cube. And again, the reason why we have to have the letter K is because it does not tell us what our constant is. So this is just writing the sentences from the equation and then writing the equation from the sentence for power models. The difference between just power models and direct and inverse variation is that now we actually have exponents on our variables. So this h could be written to the power of a 1/2, and this m is raised to the power of 3. This is what makes it a power model.